and it has a happy life and then turns into a skeleton. Similarly, if you have a membrane of a cell and the cell is dead and gets buried in a rock somewhere, if it's a robust enough molecule, that molecule might be changed a little bit, as is shown here, but it's still there unless there's some process that's really vigorously destroying it. And so, just like you would have a skeletal fossil on Earth, you might have a molecular fossil that will tell you something about Mars. And like I mentioned, there are patterns in these molecular fossils, and the patterns tend to be things that are 2 carbons apart. And so, just as in understanding whether a location on Earth or Mars is a good environment for life, you have to look at a variety of things like the chemistry or the elements necessary for life there, and so on. There's also kind of this molecular record that you want to look at, both isotopes, which I've not talked about, but then the structure of the molecules. And so this whole thing gives rise to an ecological pattern. We tried really hard to understand how to do this exploration best by going to places on Earth that might be as representative as we can find of Martian locations. So for example, next week I'm headed out with a crew to Svalbard, it's north of Norway, where there's old volcanoes that might have erupted under glaciers, kind of similar to Mars sites. We have a lot of fun up there. People carry rifles around just in case the polar bears are charging us. So
That's right.
With respect to polar bears, it's really their turf. And for the group picture, I was dressed up as men in black, kind of aliens that are invading this very pristine area. And so there's Svalbard, not too far away from the North Pole. The sun's always shining this time of year. It'll be daylight when we get up there. And it's cold, it's dry, it has different rock types and different environmental conditions from down here in mid-latitudes where life is very vigorous and really rapidly transforms everything. And so it's really interesting. You find things that kind of look like things that we observe on Mars. Here's a sandstone with these concretions there and little very tenuous light living on the surface of the rock. Things that look like images that came from Mur. I won't tell you which is Antarctic and which is Mur images, but they're kind of split 50-50 in this image. And what we do is we kind of look for these molecular fossils. We take mass spectrometers, like we're going to fly MSL, and we separate out the gases and do chemical analysis, and we see these patterns. So here's one of the world's northernmost hot springs up there, and this little green stuff growing on the surface of rocks is microorganisms. And so we can imagine that that type of environment might have existed early on Mars, when Mars had a heavier atmosphere and was a bit warmer and a little bit more friendly for life. So let me talk just a little bit about where we are in the Mars program. I kind of covered everything with just a snapshot to the left. I'm going to talk a little bit about MSL, but what's coming up after MSL is a mission that's going to orbit Mars and look for gases that are escaping from Mars. That mission is called MAVEN. And then there's really great hope in NASA that we can't do this all alone. We just don't have the resources with all the stuff that needs to be funded here on Earth to do it on our own. And so we're going to try and join forces with the Europeans, and that program is undergoing planning. The most recent thought is that in 2016, NASA and ESA combined might send an orbiter around Mars that looks for some of those trace gases, not only methane, but also a suite of other gases, and also isotope ratios, which kind of tell you something about how heavy or light the elements in those molecules are and how they get processed. For example, very light deuterium to hydrogen in water in the atmosphere might be an indication of something that's coming up from way down deep. And the normal DOH in Mars atmosphere is much heavier. It's been stripped away by the atmosphere and enriched over time in the heavier species. And then in 2018, if this plan works, both NASA and ESA would send a lander to the surface. The European mission that's been planned for some time is called ExoMars. It's a rover, and they're going to dig about 1 meter down and see what they can find. And then NASA would be sending something that was precursor to sample returns, which hopefully would follow in 2020 and beyond. So getting specifically to MSL, we have these just wonderful tools from orbit, the orbiter spectroscopy and the orbiter imaging. We're narrowing down the sites where MSL might want to look for stuff, and here's 4 of them. A couple of craters that show very clear evidence of water flow, Everswalde and Holden crater, and then a couple of spots where the signatures, the spectroscopic signatures of these really interesting minerals, probably from very early Mars are. And so we're going to kind of go, you know, the goal of the mission is not stated as we're going to go find life. We probably don't have the tools or know exactly how to do that. We don't know exactly what life way back when might have looked like even. But we're going to go look for potential habitats, things that might have been friendly to life in the past, and try and at least start to get a handle on the parameters of life. So the landing scheme is really interesting for MSL. It's this sky crane where basically the rover gets tethered down and lands right on the surface. I can show the animation of that if we have time. But the rover itself is really a huge step in capability of bringing robotic tools to the surface of Mars. The mast camera is up about 2 meters, and the wheels are kind of about that high, about half a meter high. And so this thing is really a monster rover powered by a radioisotope source that doesn't depend on sunlight to charge solar cells at night and charges a battery. And there's kind of a picture of a few people standing around a mock-up of the wheel part of this rover. And so the tools on this are, you'll be interested in hearing about, some of which are like the tools that were on MER. You have cameras on the mast. You have a microscope on the arm. There's an experiment which is very similar to the neutron detector from space that kind of saw this hydrogen at a very, very low spatial resolution, kind of hundreds of kilometers. This is a Russian-provided neutron source on the back of the rover that pulses out about 10 million neutrons at one time and then looks at what comes back. And so it can detect water ice directly beneath the rover. The tools that kind of do survey for us, some of them are similar to MER. For example, there's an alpha particle instrument that looks at elemental composition. It's on the arm. There's this really neat experiment that Los Alamos is helping develop in collaboration with French colleagues, which is up on the mast, there's a laser, and up to 10 meters away, this laser can zap a rock. And then there's this big mirror and spectrometer on the laser. And so from the emissions that come from the rock, you can really very rapidly tell is one rock different from another rock. And that's really useful because, the rocks might be covered with dust, and this laser can kind of ablate away the dust and get below and kind of really interrogate the chemical composition of the rock. And if the rock's really interesting, then we take it to what's called the analytic lab on Mars Science Lab. And half of the analytic lab is the experiment I'm leading, which is this suite of experiments that measures isotopes in organics. And the other half of the lab is really an X-ray diffraction, X-ray fluorescence experiment, which is really a definitive way of identifying minerals. And so the minerals that MER was able to find were from this Mossbauer experiment, which basically can do a pretty good job of some iron minerals, but with the XRD-XRF experiment called ChemIn on MSL, we'll really be able to nail the minerals and the processing that's happening to the minerals on the surface of Mars. So what is SAM? SAM is the experiment that we're developing at Goddard in collaboration with JPL, in collaboration with French colleagues. We have a mass spectrometer, basically ionizes some of the gas and turns it into ions. We analyze those by their mass-to-charge ratio. It has a gas chromatograph, which is a set of very, very long columns that separate out complex mixtures of gas and time, and then sends those to the mass spectrometer. And then it has a tunable laser spectrometer that JPL is providing. And that essentially looks for both trace methane and looks for, does very precise measurements of some of the isotopes. And so a really core part of our experiment, although not the entire experiment, is looking for organics. And so where might organics on Mars have come from? Well, on Earth there all sorts of stuff is coming in in the form of meteorites. We go to the Antarctic and collect